Here in this question, two tables R1 and R2 are given, and we have to find the number of tuples in R1 natural join R2. Whenever natural join between two tables is performed, the comparison will be made. The comparison on the attributes which are common in both the tables is made, and the tuples which are equal in value for the common attributes will be displayed, and the number of attributes would be union of all the attributes from both the tables. So here the number of attributes would be A, B, C, D, which is union of tables R1 and R2, and here the common attributes in both the tables is A, B. So here A1, B1 will be compared with all the AB attributes in R2. So here A1, B1, whenever match is found, that tuple will be displayed. So A1, B1, respective C value is C1 and the D value is D1, and for this one also match is found, that is A1, B1. Here C2, respective C value is C1 and D value is D2, and A2, B1, it will search for A2, B1. Here A2, B1 is not matched. So here the next tuple, next combination A3, B2 will be compared. As there is no match with A3, B2, now A4, B1 is compared. Here we found one match for A4, B1. So A4, B1, the respective C value is C3 and D value is D4, and one more match A5, B3 will be found. So one more tuple would be A5, B3, the respective C value is C2 and D value is A5, B3, D value is D5. So this is the resultant table, and it consists of 4 tuples. So here correct option is option C.
Following grammar is in Chomsky normal form. G1 is S2 AB or small a, A2 small a, capital A or small b or capital B, B2 small a. G2 is S2 AB or small a, A2 AA or small a, B2 A. Options are G1, G2, G1, G2 and none. So here Chomsky normal form means we should have two variables on the right side, two non-terminals or a single terminal symbol. Other than that, it is not allowed. S2AB is CNF, but S2 small a is also CNF. A2 AA is not in CNF. A2B is also not in CNF. So G1 is not in CNF. So we can say that a grammar is in CNF if all its productions are in CNF. As far as G2 is concerned, S2AB is CNF, S2 small a single terminal. Again A2 AA, two variables, single terminal, single terminal. So G2 is in CNF. So this only G2. Option B is right option.
GB a simple graph with 7 nodes and 1 component. Removal of a vertex from G results in maximum how many components in the resultant graph? Here it is given that G is a simple graph with 7 nodes and it is a component graph. It is having only one component. It means all the vertices are connected. The question is, we have to find the maximum number of components upon the deletion of any one vertex from the given graph. So now let us take a star graph with 7 nodes. This is a star graph with 7 nodes. If we delete this center one, this node will be getting maximum 6. Will be getting 6 components. So this is the maximum number of components which we can get upon the deletion of one vertex. So here correct option is option C.
If the degree sequence of a simple graph G with n vertices is D1, D2, so on Dn, total number of edges in G bar is. Here we know that sum of the degrees is equal to 2 into number of edges. Sum of the degrees is nothing but D1 plus D2 plus so on, D3 plus so on, dn. This is the graph with n vertices is equal to 2 into number of edges. This is nothing but sigma I is equal to 1 to n di is equal to 2 into number of edges. So here it number of edges is given by 1 by 2 into sigma I is equal to 1 to n di. And we know that number of edges in a graph, and the number of edges in a graph which is complement to the first one will be equal to number of edges in complete graph with n vertices, and the number of edges in complete graph with n vertices is given by nc2, which is n into n minus 1 by 2. So here number of edges in G bar is represented by E bar plus E is equal to n into n minus 1 by 2. So we want E bar, which is number of edges in G bar, is equal to n into n minus 1 by 2 minus number of edges in the graph, and number of edges in the graph is given by half into sigma I is equal to 1 to n di. So this will become n into n minus 1 by 2 minus 1 by 2 into sigma I is equal to 1 to n di. So here correct option is option C.
Coin is tossed 2n times to form the string of length 2n. If it is head, it is 0, otherwise 1. What is the probability of bitwise ANDing of two strings consisting of all ones? Here it is given that bitwise ANDing of two strings should be ones. Means both the strings should contain all ones. Then only the bitwise ANDing of two strings will be all ones. So here probability is favorable number of cases by total number of cases. Favorable number of cases would be here all should be tails. So there is only one way of getting all the tails. By total number of cases is nothing but here coin is tossed 2n times. So 2 power 2n. So here it is nothing but 1 by 4 power n. 1 by 4 power n, which is option C. BSTs are possible with 6 nodes. Here it is given that there are 6 nodes and we have to find the number of binary search trees with those 6 nodes. And number of BSTs with n nodes is nothing but the nth Catalan number. And recurrence relation for nth Catalan number is given by Cn is equal to Cn minus 1 C0 plus Cn minus 2 to C1 plus Cn minus 3 into C2 plus so on up to C0 into Cn minus 1, where C0 is equal to C1 is equal to 1. So if we find C6 by using this recurrence relation, we'll be getting answer as 132. So here number of BSTs with 6 nodes is 132, which is option D.